This video is going to be an introduction to analytical geometry, but specifically in grade 10. Now, just to give you a bit of background information, analytical geometry relates the normal geometry that we do in class to algebra. So you can almost think of it as a bridge between geometry and algebra. And that bridge will relate a couple of different things, but in grade 10 and 11, our main focus is going to be on the geometry of straight lines, firstly, as well as the geometry of certain types of quadrilaterals. And you'll see as we go along, when I talk about quadrilaterals, I'm talking about things like parallelograms. We're going to have a look at things like a rhombus, etc. So all the different types of parallelograms along with their associated properties. But before we can get to actually looking at examples, in this video we're going to outline the theory work. So because for most of you this is a totally new chapter, before we can begin you need to firstly understand the notation that we use. You need to look at the different information as well as the new formulas that we're going to go through. Now, all of this that we do in this video, you need to know off by heart. And even though it might seem like a lot of information at first, all that you need to remember is that this is all the theory for the entire chapter. So once we're done with this, it's going to become more of an application-based chapter. So, to begin with, let's outline the three formulas that you're going to deal with, which is distance, midpoint, and gradient. The convention that we use for writing these points out starts by us looking at any 2 points on the Cartesian plane. So if that's our Cartesian plane, and we've got 2 points on it, a point over there, and a point over there, point A, and a point B, and we know that that coordinate A will have the coordinates x1 and y1, and the coordinates of B will be x2 and y2, much the same way as any Cartesian plane. Just a bit of extra information as well. The Cartesian plane, or these xy axis that we've drawn here, is divided into 4 quadrants. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Make sure that you're always looking out to which axis is positive or negative in each quadrant. So for example, here in quadrant 2, you can pick up that we've got a negative x-axis, because this is all the negative x values, but we've got a positive y-axis. And that may help you in certain questions. So always be on the lookout for that. And in this Cartesian plane, what we're going to do is we're going to join up the points A and B. So let's join them up together. And now we can look at the properties between those 2 points. And the first one that we look at is the distance between point A and point B. So you can think of it as distance, or as most questions will ask it, as length. And the formula, which is quite easy to derive if you want to go and try it in your own time, but would tell us that the distance, and in this case you can write it as AB, because that's the name of the line. Often we will write the name of the line instead of writing distance, is equal to x2 minus x1 all squared plus y2 minus y1 all squared underneath the square root. Also remember that if you're ever trying to solve for something underneath the square root, you'll need to square both sides of the equation to get rid of that square root. In some textbooks, you'll see that they actually write this equation without that square root, and it's up to you which one you would prefer to use. The next one that we're going to look at is the midpoint formula. Now, the midpoint formula should make you think of a word bisect. Now, bisect basically means to cut in half perfectly. So if I ask you the question, where is the midpoint of this line AB over here, you'd have to look for the middle point over there and realize that that point and that point, or those two lines, would be bisected, cut in half perfectly. And we usually label the midpoint with a capital M, as shown in the diagram. And the formula for that is M, which has an xy coordinate, is going to be given as x2 plus x1 divided by 2, and then y2 plus y1 divided by 2, like so. What's important to realize is sometimes we will give you the midpoint and ask you to work out one of the other points. And the way that you can do that is simply by matching up the x-coordinate of the midpoint with this part of the formula, and by matching up the y-coordinate of the midpoint with that side of the formula. And we'll look at some examples, if you haven't done so already, where you can apply questions like that. And lastly, we're going to talk about the gradient. Now the gradient, this refers to the steepness of a line. It also talks about whether a line is going to go up or whether a line is going to go down. And you could almost think of it as if you were standing on that line. If you're walking uphill, then it's got a positive gradient. If you're walking downhill, then it's got a negative gradient. And the formula for gradient is the same one that you used in grade 9 when you were working out the formula of a straight line. And it's given to us as lowercase m is y2 minus y1 over x2 minus x1. And just to put that in perspective for you, you should be able to see that that is your change in y, and at the bottom in the denominator is your change in x. And so we can sort of word the gradient in a couple of different ways, one being the change in y over the change in x, and another one being the rate of change of y with respect to x. So how much does y change as x changes? And that becomes very important as you get into grade 11 and 12, especially if you're doing any sort of AP maths. So those are the basic formulas, but when it comes to gradient, there's two more things that we need to talk about that become quite important in questions. So the first thing that we're going to look at is when we're given parallel lines. So if you're on a Cartesian plane and you're given two lines like so, and the question tells you that these lines are parallel to each other, you can go and make a conclusion about the gradients. So we'll call this line 1, and we'll call this one line 2. And basically what we figure out is that when dealing with parallel lines, they have equal gradients. So that tells us that the gradient of line 1 will equal the gradient of line 2. So parallel lines have equal gradients, and this is the formula that you can put together for that. The next thing is when we're given perpendicular lines. So let's say we're given a case like this, where we've got a 90-degree angle between those two lines. We now know that they're perpendicular to each other. And similarly, we'll say this is line number 1, and this is line number 2. And when we put that together in a formula, we get that the gradient of line number 1 multiplied by the gradient of line number 2, you can see they're in brackets, so they're multiplied, is equal to -1. So that's quite an important formula to work with. And then the last one, and this isn't so much a rule on its own, but I think it's quite important to discuss, is that if we're given a line anywhere on a Cartesian plane, and we're given a number of different points along that line. So let's say we're given a point over there, and a point over there. We'll call them points A, B, and C. If you need to prove that the points are collinear, all you need to do is basically prove that the gradients between the points, between those points, are equal. If you can prove that the gradients between the point A and B is the same as the gradient between C and D, then you know that those lines, or those points rather, are collinear. They lie on the same line. All of this does relate back to the equation y is equal to mx plus c. So later on in the year, when we deal with straight line equations, a lot of this will come back, and perhaps even in your final exams, we'll begin to mix all these different parts together. So that's the video just on the beginning theory part of analytical geometry. Go take some time to study this, to learn this, and then watch the second video on an application type question for analytical geometry.